All right, we're on the home stretch. We're going to talk about solids briefly. A lot of this relates back to the previous information about melting point and heat of fusion, heat of blank from the talk about liquids. But basically, if you have a high melting point, you have a strong attraction for another particle around you, which means that you have a strong intermolecular force. So this is directly related. Heat of fusion is just the transfer or the physical state change between it's melting, so it's between solid and liquid. So if we're talking about heat of fusion, it's the energy needed to change 1 mole. This is usually in kilojoules per mole. Same, it's directly related. One extra thing that AP has put in this year is polymers. So I'm pulling from my background on biology to talk about the intermolecular forces between large molecules, which we call polymers, which are just made of many, many monomers. You already know a lot of these because you took biology as well. Monomers build polymers. So the first example here is of DNA. DNA, you know, is a double helices, and it's got 2 big DNA strands, or strands of a single helix made of nucleotides. So each of these nucleotides is 1 monomer. They have covalent bonding on their backbone, on their backside, but in the middle they have hydrogen bonding. So these nucleotides A and T, C and G are going to be bonded together weakly with hydrogen bonding. But it's not so weak that it just falls to pieces because it still exists in its double helices form. Hair is another example. You can see my picture here to the right. We have multiple forces between particles of hair, which is just a polypeptide. Polypeptide just means multiple peptides, which is another word for amino acid or protein. So pieces of hair are attracted to one another, or can make your hair different shapes, curly, wavy, straight, based on the IMFs they experience. They have hydrogen bonding, ion bonds, quote unquote bonds, they're just attractions, or there's actually a bond called a disulfide bond. That's not an IMF, that's an actual bond between 2 sulfurs. Lastly, we have to talk about how these IMFs are forcing the structure to appear differently whenever different IMFs occur in different parts of the same molecule. So the same molecule can mean that DNA has all those little hydrogen bonds between it, and it's between two single helices. But a protein's different. A protein has a massive structure. So here's the polypeptide chain, and this polypeptide chain is attracted with itself in multiple places. We have a hydrogen bond here. We have a hydrophilic interactions in some places. We have a disulfide bridge or disulfide bond. We have ionic bonds. We have got lots of stuff going on, but it's all within the same polymer. So this causes this polymer to take on a specific shape. We have to know this because the shape drives the function of specific biomolecules. So the IMFs are going to hold it in the correct shape, which would therefore allow it to function appropriately. If we change the shape due to changing the IMFs, then the function is not going to be sufficient. It's not going to correctly perform in the body. There's another picture here that says the same thing. So they're big on using some biological examples, so I wanted to use that here. Okay, so let's briefly talk about these things that we already have prior knowledge of and talk about the main attraction or interparticle attraction that's present. So the first thing that I usually do is identify, and then I'm going to find the IMF, or IPF as I'm going to start to call it, within each of these. Well, this is a metal. Metals undergo metallic bonding. That is an actual sea of delocalized electrons that's attracting to itself. It's an interparticle attraction. HBr has a dipole, so this is a polar molecule. This polar molecule is going to undergo dipole-dipole interactions. SO3 has 3 ligands. Sorry about that. And you notice now that it's got a nonpolar structure overall. This nonpolar structure allows it to experience London dispersion. Neon is just an atomic structure. Atomic structures with itself can actually undergo far it's nonpolar because it doesn't indicate any reason to be polar, so it can experience with itself London dispersion forces. KCl is ionic, therefore it's going to undergo ionic bonding, which is an intramolecular force. Cl2 has an equal distribution of electrons. There's no dipole moment, therefore it's nonpolar. It experiences London dispersion forces. CH2F2, this is one that a lot of people mess up because they expect for the dipoles to cancel with each other. I'm not drawing all the electrons, but you should. You'll notice that there's two areas here, one which is partially positive overall, this side of here is partially negative. Any way you look at it, this tetrahedral structure does not allow for cancellation. Therefore, it's polar, and since it doesn't have hydrogen bonding with O, N, or F, it has to be dipole-dipole. H2S looks like this. It has a bent structure. This bent structure causes it to be polar, and since it is polar, it undergoes dipole-dipole. It does not have the ability to hydrogen bond. Ammonia, we all know this one. It has a trigonal pyramidal structure. It is polar overall, and since it has hydrogen bonding to nitrogen, that dipole is very, very large, and therefore it's hydrogen bonding available. This is something you've not seen in a while. It's got 1, 2, 3, 4 carbons, and all the carbons, if you draw it out, are singly bonded, so that's butane. Butane is a long, single, straight chain. This straight chain of carbons has no difference in polarity anywhere, therefore it's going to experience London dispersion. Last bit here, we've got sulfur dioxide. Sulfur dioxide looks like this. So there's octet on everyone here, and it's bent. This bent creates a polar structure, which experiences dipole-dipole. Last bit here, we've got an alcohol group. An alcohol has a O singly bonded to an H. This bit here is able to hydrogen bond. So that is the main force there. So all of these contain London dispersion. However, the most significant one is the one that we have named. We're going to talk briefly about these crystalline structures. We're going to go into a lot more detail tomorrow about network covalent solids, etc. But I want to briefly introduce you to ionic crystalline lattice structures. This is a good picture from your book. This chart you've already done the majority of. You already have all the properties and examples indicated. I recommend you just write down or fill out the part with network covalent and molecular solids in addition to the stuff below the chart. So I'm going to scroll up until I see just the stuff I want to see here. Okay, so we're going to talk about network covalent and the fact that they only are including atoms, which I'm going to go to so you can see the top part of the chart here. They're only including atoms, usually carbon or silicon. Carbon or silicon. So those are the particles that are at the lattice points. And this does not actually have a lattice feature because it has the ability to form a network of shapes. Since it's network covalent, it definitely contains covalent bonding. And one interesting part of this is that since it has a network, a vast array of bonds, it has an extremely high melting point, and it's very hard. An example of this is diamond. You'll notice that graphite is here too, except this one's a soft version of diamond, I guess you could say, until we get into the extreme detail. Silicon and silicon dioxide, which is quartz or sand, is also very hard. So those are some good examples of that. We're going to go into detail about the features of this later. One more is the molecular solids. These molecular solids can come in two varieties. They can either have molecules at their lattices, so like water or carbon dioxide, or it can have an atom at its lattices, lattice points, which in this case could be neon, it could be argon, some sort of single element that's going to create some attraction with itself through London dispersion. So London dispersion is a big factor here. In this one, the molecules can definitely undergo dipole-dipole interactions. Both of these feature a low melting point though because of their London dispersion. Atomic solids, like I just was talking about here, have a single element that are going to be at each of the lattice points, and so network covalent will contain the carbon and silicon mainly. Atomic solids can be metallic solids, which you've already heard about, which will contain any of your metals. And then you can have the argon and the noble gases, which would be mainly represented in molecular solids, but it's still a single atom. Metallic bonding, we've talked about before. Network covalent, we're going to talk about them being giant molecules and creating a network of directional covalent bonds. This is just an introduction since it is your reading guide, but we're going to go into a lot more detail tomorrow. Group 8A solids are those molecular solids that I just talked about up here on the table, and they're the ones that are having the lowest melting points possible. So there's two different types of atomic solids. The high melting point ones, like the ones with metals, and then the low melting point ones are the ones with the noble gases. We've talked about the interparticle attraction of ionic bonding. I just want to remind you it's a lattice structure or a crystalline structure. At each point, you have ions. These ions are causing an attraction to their neighboring ions through Coulombic attraction. And remember, the charge density or the charge product is the most important feature here when we're talking about the electrostatic attraction. Each structure, each crystalline solid has a structure called a unit cell. It is the smallest repeating unit. So if I was over here on, this looks like sodium chloride to me, we've got a cube. I'll try to trace it where you can see it. That has a lattice arrangement. So a unit cell is simply a square, and in this case it's got ions or atoms at each of the breaks at each of the points of the cube. So it's going to reflect the stoichiometry of the solid. So this very well could contain a 1-to-1 ratio of Na plus and Cl minus, whereas something like calcium chloride is going to contain 1 calcium for every 2 chlorine ions. So it depends on which structure we're talking about as to what the the unit cell looks like. The lattice is simply a repeating nature of this unit cell. This gives these lattice structures different overall large-scale shapes. We've seen this in probably a lot of the like dehydrating some solids that we've used. Copper 2 sulfate, for example, always forms a shape like this, whereas calcium or sodium chloride doesn't form a trapezoid like that or a parallelogram. It's going to form a different shape. So you can read through this information. I used to talk a whole lot more about unit cells, but we're going to touch the basics about how each of the corners of the unit cell are going to contain the particle of interest. The identical particle in this case is going to be an ion, and different shapes can come from these building of the unit cells. One more thing is that we also talk about the faces of the unit cell and the body of it. So sometimes we're going to call these structures by the name indicating information about the face or the body. So here's some examples. Simple cubic means that you just have atoms at the corners, and that's it. Face-centered cubic means that you're going to have an atom that's present right here in the middle of the face. Body-centered cubic means that inside there is an atom, and it kind of shapes the rest of the crystal around it. I have more pictures on the next slide. So the simple cubic, the body-centered, and the face-centered. You can see the pictures here indicating simply that. Simple are just there's points at each corner. Body-centered means that you've got a huge atom in the middle, and then there's other atoms that actually are just, this is a cross-section, so it's cut off around it. And the face-centered means that you have a hemisphere here that's stuck in the face. And you can look at the different information here on unit cells. It's basically memorization about how the structure arranges itself, and I have some pictures about different types of compounds. This is the copper 2 sulfate crystal that I was telling you about. So look at this. I'm not testing you on the particles, the number of particles, or specifically how to draw them. I just want you to be aware of these 3 different types. And that's it.